The broadcast is now starting. All attendees are in listen-only mode.
I hope I am audible.
Yes, sir.
Okay. Thank you very much for the introduction. And thank you everyone who is participating in this webinar. As Vimal introduced, this is a series of webinars under the CII initiative on manufacturing and digital excellence. So it's my privilege to be here to share Saint-Gobain's experience on this digital manufacturing and Industry 4 platform on which we have started working on about a year back. I'm very happy to share this particular topic, whatever we have done so far in this important topic of monitoring OEE in the shop floor to be able to drive improvement. As was introduced by Vimal, I'm basically a mechanical engineer who spent a lot of time in the shop floor where we used to keep records manually and then do analysis of losses, typically at the end of the year or end of the month or end of the week. From there today to be able to monitor the machine as it runs, to be able to get data in real time in the shop floor on large terminals and be able to continuously drive the performance. It's really a big step change and I'm happy to be here, as I said, to present our experience in this domain. So with this introduction, let me set the context for this presentation by sharing few slides on what's happening in manufacturing in general, how digital is really transforming the manufacturing, and where our topic of this real-time monitoring fits in the overall digital portfolio. So, as you all know, manufacturing continues to evolve. Vimal, my slide has changed. No, there is no problem in. Hello. I hope the presentation is moving forward.
Yes, sir. Yes, sir.
Manufacturing. Sure, thanks. Being the first slide, I just wanted to confirm.
Yes, sir.
Manufacturing continue. Sure, thanks. Manufacturing continues to evolve. As you know, in the last 3-4 years, we have several new digital technologies coming into play in the area of manufacturing. Thanks to the new innovative materials, the new processes like additive manufacturing, what you are seeing in the screen, where manufacturing is always referred to removal of metal or cutting, removing metal from a stock bar to create what you want, to creating something from nothing, basically to build whatever part you want through the process called additive manufacturing or 3D printing. So this is a new evolution with the digital technologies, and the manual labor is slowly giving way to robots, which is not something new, but we also see the emergence of new type of robots which are called collaborative robots or cobots, which work along with people. So it is not replacing people, or it is complementing people. They learn very fast from the people. They work along with the people, and they learn. So here you see a picture of some operator teaching a cobot to perform a particular operation. So these are new generation equipment which are coming into picture to alleviate the physical labor. And then finally, from mass production to mass customization. Today, people don't want standard products. Everybody wants products to be customized to their own wishes. So we are moving from an era of mass production to mass customization. This is very clearly seen as trends in the manufacturing that's happening today. And the manufacturing process itself, they go through a series of revolutions. I think this slide, many of you are aware that starting in the 18th century with the first industrial revolution, when the first machine tools were introduced, to the 19th century, 1870s, where the mass production was introduced, and 1970s saw huge industrial automation in terms of CNC machines coming into play, etc. Now into the 2000s, where we see the fourth industrial revolution, as we call it, where we see the internet and several things that are getting connected to the internet. That's what we call as Internet of Things. So we are seeing now a lot of connected enterprises where it's not just anymore disconnected equipment or disconnected lines. So everything getting connected seamlessly, sharing information in real time, leading to several improvement opportunities across the manufacturing spectrum. So this is what we are seeing. We are at the beginning of an era which we call the fourth industrial revolution, where the digital technologies are really taking the manufacturing to the next level. So ubiquitous connectivity. So this is something which is really driving the digital wave. So I used to always in all the meetings or presentations, I used to ask, what is this digital all about? Digital has been there for so many years. It's not something new. The word digital has been there for a very long time. So why it is coming back again? What is the new buzz about this digital? So what is digital in today's context is your connectivity and mobility. The all pervasive internet in the form of mobile internet is really revolutionizing the way we look at information, we share information, we control information. So this web plus mobile is the new digital. So, and this is driving big changes. The Internet of Things, as I was saying, and as we are seeing in this picture, the whole lot of things. It can be sensors, actuators, measuring devices, robots. So many things are getting connected, and they are creating a new dynamic, self-organizing, real-time optimized and value-added connections across entities. So these are not anymore standalone. They are getting connected very easily using the all-pervasive internet today to form self-organizing value-added networks. So to give a simple example, today a machine on the upstream can get information from a downstream machine or vice versa about the progress of production, about the quality of production, etc., so that they can change their parameters or adjust themselves so that the production process is uninterrupted and the quality of product is maintained. So such connections are today possible, and this is what is really called digital in manufacturing. And the Internet of Things, as we see, it's not just to connect equipment, but also to derive value out of it. It's according to a McKinsey survey, recent survey, it has the highest potential in manufacturing. The IoT, or the Internet of Things, as you can see from this slide, it's having a tremendous opportunity. I mean, much greater than any other area. Like people talk about smart cities or retail, or where digital can be used, but factories have much unexploited potential, and that's going to be really driving it big. So this is where we also started at Saint-Gobain about a year and a half back to really start exploring the opportunities around this digital. So we have identified several areas, as I'm listing here, starting from real-time monitoring, shop floor KPIs, quick reaction to deviations, and process optimization. And I think many of these things are even, being tried by many other companies. We are not unique in that sense, but everybody is trying out these areas of opportunity, be it digital plant operations, predictive maintenance, digital learning, smart products, and traceability. So I have just listed various areas where most of the industries are now working to exploit this new digital technologies. So in this, we have chosen today the topic of real-time monitoring, in which we are going to specifically see how one can build simple digital tools using components available off the shelf in the market, low cost, and the companies like IT department and the maintenance or the technical department or the instrumentation department. In various companies, they call it in different names. They can join together, build a simple network to really acquire data from their existing equipment, and then be able to analyze and then present in real time to the shop floor manager, so that the agility of the shop floor decisions are improved. So this is what we are going to see today. When I talk about digital tools, simple digital tools, what does it mean? What was not existing? What was not existing in the past, and what is available today, and what is driving this big change? In the past, whenever you need to connect to a machine or already a numerical control machine or a CNC machine, you can't do it very simply. You'll have to normally going back to the OEM, asking for any modification to be done to be able to capture data for whatever purpose that you want to take it out for. But today with the availability of simple tools, sensors and microcontrollers, and the easy availability of pre-built codes. Programming was earlier difficult, but today you get code very freely on the internet. So by using available standard hardware components and software components, and with a little bit of perseverance, the local IT functions in various factories can also start building simple tools to do effective monitoring. I mean, it can be, there are a number of opportunities, as I listed. In every area, there is an opportunity for IT and the function to come together to really build value-added tools for the organization. So this is one of such tool what we are going to discuss today to monitor the equipment effectiveness through simple digital tools. Okay, so why measure? It's need no explanation. Anything that you want to improve needs to be measured first. So Peter Drucker once famously said, "What gets measured gets improved." So in this context, I think many organizations, many of you are here, are already pursuing TPM, and OEE is not something new to you. I don't have to talk about OEE a lot, but just to read, and I think there are many other participants, maybe from academia, who may be new to this concept, and many people from IT functions in various organizations may also be listening to this webinar. So I just will talk about OEE at a very high level. I will not go in deep. So at very high level, so that everybody gets to a common understanding what is this OEE that we are going to talk about in this webinar, before I get into the digital part of it. So our aim is to measure overall equipment effectiveness to improve the same. So what is this OEE? It is nothing but to understand how effectively an equipment is used in relation to its full potential. So a simple explanation of OEE is this. So all the words that are highlighted are important. So utilization of equipment in relation to its full potential is what we call as a OEE. Here the equipment can be an individual machine, or it can be a whole production line, doesn't matter. Whatever physical structure that produces a useful output is called an equipment. In a discrete factory, a lathe can be an equipment, or a drilling machine can be an equipment. But in a process industry like a cement or steel or a glass, the entire line is together called an equipment, where we need to measure this OEE. So with this simple explanation, let me get into the slide. So why this OEE? What's really happening? So what is impacting the utilization? Of course, in manufacturing, you have losses. Everywhere you can have losses, which can reduce the utilization of an equipment. And it is important for all of us to have an idea about the losses in a systematic way, so that when we measure what we have to measure to capture the OEE, that we are able to work on each of these losses and then take up projects and see ways of reducing these losses. The whole idea of measuring is to reduce losses and then improving. So in that context, I'm just putting the 6 big losses. This is a very standard term used in TPM. Those in academia, or those who are not very familiar to practicing this TPM in the shop floor, they can get a lot of resources from the internet. It is very important to learn this in a structured manner. So these are the 6 big losses. Machines all the time, you can get broken down. There can be failures, tooling failure, unplanned maintenance starting from there. And also you stop the machine for changing the production, changing the components. So you keep making minor adjustments to compensate for tool wear, etc., or to improve quality. Then machines may not run always at an optimum or a designed speed because of various reasons. Maybe the vibration levels are high, or the environment is not good, or there can be any number of reasons. The equipment may be old. Though the equipment is designed for running at a given rate of speed, you are forced to run it at a lower speed because it is not in good condition, which is actually leading to a loss of performance. And then equipment always don't produce good quality product, so you can always have rejections, again due to various reasons. And then whenever you set up and whenever you change, you are likely to generate some scrap, because you'll be trying out till you reach the correct dimension. So the scraps can be on that front. So these are the 6 big losses, including the small stops for various reasons. So it is very important to understand these 6 big losses. Why? Because as we progress, as we measure, as we start building the digital tool for measuring OEE, some of the events you will be able to capture through the sensors and whatever you are going to put in the line. But you may capture the event, you may capture the time of loss. You may from the sensors you will be able to exactly tell, like the machine was stopped between 2:45 p.m. and 3 p.m. But you also have to have a system to capture the reason for this stoppage, so that your reporting and analysis can be perfect. So in that context, it is very important for us to understand what are the different type of losses that can occur at different stages, so that when you develop a system, you build these losses or the reason codes for losses that can happen in your own production process through a computer system. So when the operator is performing an operation and there is going to be a line stoppage or something, so he's able to justify, or he's able to record the correct reasons, so that at the end of the day or end of the week, when you do the analysis, you are able to see the reasons for various losses and take corrective actions. So it is important for us to understand these 6 big losses. Then when it comes to OEE, what are the things that you measure? Before you go into building the tool, we need to understand what are the things that we measure. There are 3 big measures of equipment utilization. The first one is availability. First, the machine should be available for production. Imagine a shop floor, imagine a machine shop where it runs in 3 shifts. That means 8 hours shift, 3 8-hour shift. And imagine one particular machine. Okay, so the machine may or may not be available for all the 8 hours due to various reasons. Okay, you may have planned to run it for 8 hours, whereas you may have some downtime. It may be planned downtime, a scheduled maintenance, or a unplanned maintenance, which we call the breakdown. Or you may have to do some major setup changes. You change from component A to component B. You have to remove a fixture, refit a fixture, do the setup, change the tool. So all this make losses. So though you have planned to run the machine for 8 hours, you actually have only let's say 8 minus 1 or 2 hours, like basically if you have stoppages. So the available time is reduced because of this reason. So this is the first thing that we measure, how much the machine was actually available in a day or in a shift. So this is the availability factor. The second factor is performance. Okay, the machine has been available for X hours during a day. It may be 8 or less, but it was available for X hours. Okay, while it was available for 8 hours, were we able to run the machine at its rated speed for all the 8 hours or not? So this is the next measure, whether it was performing at its peak or at its designed speed. No, I was not able to run it at full speed because of various reasons. My tool was not good. There was too much of vibration, and then so I had to reduce the speed or reduce the feed. The raw material was not good. So to various reasons you are reducing the speed or the feed of the machine. So you are not getting the desired output. Normally, for every product that you produce, for every operation you do on a machine, you have something called a cycle time, which you are all aware. Like my production rate will be based on my cycle time. Suppose my cycle time is 30 seconds. So I produce 2 pieces every minute. So this is my rated production. But if I'm not operating the machine at the full rated speed, I may not get 2 full pieces per minute. I may end up producing only less than 2. So this is the loss of performance. So the second thing you measure after availability is the performance. And the third one is quality. Okay, though I produce at a rate which may be a design rate or something below the design rate because of my machine performance, I still may not produce every piece as a good piece. I make, let's say, 100 pieces. Then I lose maybe 10 pieces due to bad quality or during the setup. So my actual good production is only 90 pieces. So this is the third thing that you measure. So how much the machine was available to you, though it was rated to be available to you for 8 hours, first measure. The second measure, though it was available for, let's say, 7 hours, I couldn't run it at full speed. There was a loss of performance, so that's the performance factor. And the third one, though it was working, I was producing, but I still ended up producing bad quality pieces. So there is another loss of performance. So these three are very, very important to keep in mind: availability, performance, and quality. These are the three factors which are going to determine the overall equipment effectiveness. So let me go to the next slide. So how do we compute? To be, following a standard formula, everybody uses one computing model. Okay, it's a very simple one based on what I just explained. Okay, you have a total operating time. So if you have available time A, and it's not, there is a time for which it is not scheduled for production. It was stopped. Maybe the machine was running only 2 shifts instead of 3 shifts. So something is lost because it is not scheduled for production. And out of the time that it was scheduled for production, there was a failure, there was a breakdown, or there was a setup change, so the machine was idle. So the running time is the available time less the failure time. So this is the first availability factor. The second one, okay, out of the available time of B, I should have produced, as per the standard rate, I should have produced X items, whereas I really ended up producing Y quantity because there was loss of performance. There was minor stop due to various reasons, and then there was speed loss due to non-performance of the machine. So these are the two other factors which determine the performance. And third one is the real production, what I produced, and then less the scrap or rework which I generated. I ended up producing only F good products. So putting all this together, this is how the OEE is computed. Availability is computed as B by A, running time by available time. The performance or the efficiency is computed by D by C, real production by theoretical production, and then the quality factor was computed based on F by E, which is good products by real full production. So multiplying all this together, you get the OEE. So this is the background to the OEE computation, and most of us use this formula to compute the OEE. To put it all together, so we measure three things before we start getting into the digital tool. we clearly know what we are going to measure. We are going to measure three things: availability, performance, and quality. And let me tell you that you may not measure everything digitally. Okay, your time availability, you may be measuring through a computer system. Suppose if you have a scheduling system, you may say it was available. The machine is going to be available for 7 hours only because there is a planned downtime of this. You can also indirectly compute the availability by constantly monitoring the machine run hours. So this is, if there is no other method to measure, you can use a simple tool, simple encoder to check what is the time during which the machine actually is running and when it is stopped. So you can also compute the actual running time. So in whatever we are going to see, there is no single method. So you have to devise your own method, what you want to really measure, and then use the ideas that we are going to present today to suit your needs. Okay, what we are going to speak today is how you can use sensors and the other hardware items which we are going to show to really capture events or to capture the speed or capture whatever happens in the line, and then use it in your own process environment the way you want to compute. Okay, so we are going to measure, typically we are measuring three things: availability, performance, and quality. Okay, so before you start, you need to know what you are going to do. So I'm putting the whole thing in perspective for this project. So you will start planning. You will choose an equipment. Then you will choose a metric, what you are going to measure. It can be a runtime or a downtime, or it can be a part count. It can be the line speed, anything. So each is a metric. And then what method you are going to use for measuring, and then what tool you are going to use for measuring, whether you are going to use a proximity sensor or an image sensor or a weighing scale. So there are many different type of sensors or measuring instruments that you have to use depending on your product and your manufacturing process. So there is no single solution for every type of manufacturing process, but this method, what we are talking in this slide, the thing that you have to plan, your equipment, your metric you are going to measure, and the method of measurement, and the tools, hardware, etc., what you are going to use for measurement. So then you actually do the measurement. So in the doing part, we capture the information, we capture the event, we capture the data, and then we store it in a database, and then we analyze and compute. In each case, you may have to compute. Maybe if you are counting the parts by 2 proximity sensors, you have to count by discounting the signals, like when the part passed through signal A and when it passed through the signal B, then you know, okay, one component I have completed. Like that, for each process you may have different method. So you have to really store data, capture the events and store data in a database, analyze and compute the metric that you want to measure. Then the third one is checking. Okay, so I computed, and then how do I present? How do I review? How do I make sure the managers see it? So you provide check dashboards, reports, and in some cases alerts to really provide this information to the decision makers, and then act. Act part is once you know this information, you have the dashboards and reports, then you start improving. So you cut losses, you continuously monitor in real time, and you benchmark against similar equipment or a similar production line, and then continuously improve. So I have just presented what we are going to do, or what every typical manufacturing company will do to improve. So it's a PDCA cycle, and we are also putting our own project of this OEE measurement and monitoring into this PDCA cycle, and we will progress in the same fashion. Okay, now let's get into the real topic of this presentation. How do we build a simple digital tool to measure the OEE in a typical equipment? So let me start by, because we are going to talk digital, before we get in further, I want all of us to have a common understanding. So I'm sure many of you hearing this presentation, you are aware of this layers in manufacturing IT systems. There is also a ISO standard. So it starts various levels. So at the field level, or the level 0, you have various electronic components like sensors, actuators, IO devices, measuring. So these are actually in the field, on the equipment, in touch with the products that are being produced. These are the actual endpoints which really measure or monitor what is going on in the line. So this is the level 0, and then there is a level 1, which is the programmable logical controllers, distributed control system. So basically they aggregate the signals from the level 0 devices in various registers. As you can see, there are many different type of PLCs. They collect this information electronically as signals, and then they also are used to control these devices. See, as you know, you have a sensor and you have an actuator. So in a sensor, you can take an input from the line, you can read some data, and then you send some command to the actuator to do a particular task. It can be open or close. So you have both. So the logic controllers are programmed to both read data and then send data back to the another device to perform a particular action what is desired. It can be to increase the speed of the motor or decrease the speed, whatever. So these are the tasks of the PLCs. And then at level 2, here is where the human machine interface comes. The PLCs are simple hardware with no screens or anything. Sometimes you may just have PLCs and you do programming once using an external device and then you forget, the machine runs. But in sophisticated lines, you also continuously monitor what is happening in the line. So you have some interfaces, human machine interface. Then SCADA. SCADA is a supervisory control, and so it gives you a opportunity in the control room. Many of you may have seen a control room. So you can see the people constantly monitoring process. They use what are called the supervisory control and data acquisition systems, which continuously acquire data from the line and then present them in different graphical formats, showing the alerts and then allowing people to control the equipment through a simple HMI. So these are coming in the level 2, and the level 3 and level 4 are more of information systems, where after the event happens in the shop floor, so the data is sent to the higher level systems like MES. MES is a manufacturing execution system, which can actually start recording what has actually happened in the line, how many pieces of products were produced, and what was the line parameter. So, and then ultimately to the level 4 systems, which are ERPs and things like that, which aggregate information even at a higher level. So these are the 5 levels of information systems or the layers that exist in manufacturing IT systems. And in our project, I think we'll be talking more of starting from level 0 to level 2 or sometime to level 3. So our OEE measurement starts with level 0, where we put some sensors in the line to check what's going on, and then aggregate this information and take them out of a PLC or even directly from a sensor into a microcontroller, and then pick up this data and store it in a database, do computations, and present the OEE to the manager. So this is what we are going to do. So, and what are the different type of level 0 items that we are seeing from a OEE perspective? Okay, in OEE, you need to really sense the events or measure what is happening in the line. So the sensing can be done using different type of sensors, which are required for different type of manufacturing process. So if you have, for example, the first one, a capacitive sensor, which really knows that something goes closer to that, it can sense the movement. So this can be fitted in a conveyor, for example, when the parts are moving over the conveyor. So as each part moves over the conveyor, the sensor knows that, okay, something has moved above me. Then I send a signal to the connected relay saying that I sense here a movement of a particular movement of an item. So then you start counting. So for each movement, each component that passes over the sensor can send a signal back to the relay saying that, hey, I counted one number, like that. So this is an example. The second one you are seeing here is a reflective retroreflective sensor. This is a slightly sophisticated sensor, again, which uses the light to really send the beam and then take it back. So it can also, apart from measuring the simple movement, it can also measure the speed of movement, etc. So this is another type of sensor. Then you have some thermal imaging camera. Even a camera is a good sensor. In many of the processes, a simple camera is used for sensing what's going on in the line. Is there a part on the conveyor? Is it moving? So these kind of things are also interpreted by cameras. It can be a IR camera, or it can be a thermal imaging, or it can be even a laser. So there are different type of cameras there. Then there are vision sensors, again, which are again using laser kind of rays to monitor motions and then start counting them, including the distance at which the part is moving, the speed at which the part is moving, etc. And there are load cells which can measure the weight of a moving product in real time. And there are drives which again are electronically controlled, which can be controlled very precisely, where you can also get a feedback about the speed and the current that is drawn, so that you also know what is the load on the motor. So these are different type of sensors, and you will choose a sensor which is suitable for your own process. So this is the first and foremost list of items that you will be interested before you start building a digital tool. Second one is, okay, you have sensors, then you have to pick up data and then put them onto some data concentrator, which can connect to different type of sensors and pick up data through various data communication protocols. In the shop floor, there are different type of equipment from different OEM. They communicate using different protocols. So again, these are some of the examples of aggregators which can connect to the different type of IoT components in the line, like sensors or actuators, and then they can read and send commands. So there are some examples here. So in many cases, you may need a IoT gateway or aggregator, and then at a slightly higher level, you already have PLCs and supervisory controls. In some cases, or in many cases, if you already have a sophisticated line, if you already have a line which is equipped with a PLC, then you may not even put a new sensor in the line if it is not really required. So you may even be able to connect to the existing PLC and then read information from the PLC and directly take it for processing without putting additional sensor. This is also possible in some cases. You have to check your own process. So PLCs are another layer. And then the new generation of microcontrollers, which is making things very interesting today. So today we are going to talk a lot about these microcontrollers, because here is where building your own digital tool comes into picture. See, as I said, if your line is already equipped with a variable drive and then a PLC and a SCADA and all that, you are not going to really think of building your own tool. Most of the information that you want to have is already available in your system, your own system. You are not going to really take it out. But in many cases, the machines are not really equipped with PLCs. So you have a lot of conventional machines. You have discrete machines. You have different type of processes. Those people are really interested to know how, without investing a lot on OEMs and on PLCs, etc., how do I, using simple sensors and simple off-the-shelf items available in the market, how can I build my own digital tool to get what information I want? So that's where this kind of microcontrollers come into picture. I think a lot of the companies, a lot of people are using this Raspberry Pi, which is a simple microcontroller, or it is nothing but a small computer. It comes its own memory, its own ports, and it has its own operating system and also a lot of software on that, which are listed here. You can do programming, you can run Python, for example, Python script, you can run on it, and there are multiple databases supported on all this. come at a cost of 3,000 to 3,500 rupees in a small package. And that's what really making things very attractive for people to try and build their own digital tools. And this is what we also and many companies also trying to build now. So this is one important element of our whole experiment. So we are going to use Raspberry Pi in our presentation today to see how to connect things up. Okay, the next one. So this is what is getting done most of the times. So the Raspberry Pi microcontroller comes with GPIOs, which are input-output pins, where you can pass on signal, and then you can read the signals from a program which runs on the computer. Basically, you have ports or memory addresses which can be monitored by a script which can continuously scan this memory, and then detect if there is any change in the state. So this is what we are going to do today. So you have signals processed by the sensors connected in the equipment, and the signals are picked up by a relay and then transferred to the microcomputer board onto a pin, which you can see on the right side at the end point. You see the microcontroller pins on the Raspberry Pi. So this is expanded and shown here. You can connect up the relays to the microcontroller board, and there are hundreds of projects which are listed on the internet. If you go to the Raspberry Pi site, you can learn. People who are inquisitive, people with a little bit of knowledge. It doesn't really require great electronics knowledge. With a little bit of interest, you can really find hundreds of projects which are done using the Raspberry Pi microcontroller and off-the-shelf sensors and whatnot. So we have just used one of such ideas, and then that's how this has been developed. So now coming to how we actually do measure OEE, or how do we actually use this setup to measure what we want to measure to go to the OEE part. So in our case, for example, I'm starting with an example where I have a conveyor where a part is moving. So and some process is performed on the part while it is under the spindle of the machine. So there is a sensor which we put at the incoming stage when the part really enters the machine bed, and there is a sensor on the outside when after the process the part moves out of the bed. So you have a sensor 1, and then there is a sensor 2 which shows the glass input and glass output in our scenario. So there are 2 proximity sensors kept. So as the glass moves over, the sensor 1 and sensor 2 start counting the parts, send the signals to the relays. So when a part moves over the sensor, so the sensor are connected to a relay, and the relay opens or closes based on the signal sent by the sensor, which is picked up by the microcontroller. The relay is connected to the GPIO pins as I showed in the previous slide, and then there is a Python script which is running continuously in the microcontroller or the Raspberry computer, to check the status of these pins. So this program, the Python script, can continuously scan and read changes in the state of the GPIO pin. The moment there is a change of state, that means the relay has passed on a signal saying that the proximity sensor S1 has sent a signal. That means one part has moved over. Then the program can register, okay, S1 has sent a signal at this point of time. And then it looks for a corresponding signal from S2 and waits for the corresponding signal. So when the S2 sends a signal, then you know one part has moved in and moved out. So using these two events, you can capture a lot of data, like how much time it has taken to get the signal from S1 to S2. That means the cycle time of this component on that bed is the time of S2 minus time of S1. So this is one. And number 2, in a period of, let's say, 4 hours, how many times I have received the signals? So actually, what is the count of parts that I have gone through? So I know the theoretical time. In 8 hours, I'm supposed to have received, if the cycle time is so much, I should have received so many counts, but I have not received so many counts. That means there is a loss of production. So what is the loss? So the system can compute automatically, hey, I have not received a signal between 2:45 and 3:15. So what happened during this 30 minutes? It asks the operator to tell what happened during this 30 minutes. The operator has to select a reason code why there was no production during this half an hour time. So just using these two sensors and capturing the signals, you can build a lot of information using this program on a simple tool. And then the data from the microcontroller is pulled through a firewall into a server which is kept in the plant network. So the firewall is to ensure that the information is very well encapsulated between the industrial network part and the other plant network part, because today this is one important part of the cyber security. You cannot pass information from the open internet or open network into the industrial network, which can really corrupt the industrial control systems and make problems in the production equipment, which is not allowed. So you put a firewall between the industrial network and the plant network to allow signal to only pass through one way and to specific ports from A port to B port, and then only specific protocols or specific ports used by specific applications. For example, if I am using MySQL database, I need to open only a port, a particular port, let's say 336 site or something, TCP port. So such rules can be built into the firewall, which is very, very important. When we try something like this, we should not get a blame saying that, oh, you connected the machine directly to the network and some virus has flown into the industrial network and my CNC computer is down. So such nuisance should not happen. So we carefully isolate the plant network and the office network. And then once the data comes into your office server, then you can build your own application. It can be running on the web, it can be running on a mobile, anything. So we have several applications. So first thing, we put the data that is picked up from the line. We build a dashboard using a web development platform, and then we show the dashboard on a large monitor in the machine, near the machine. So the machine supervisor or the line manager can see, by standing near the machine, they can actually monitor what's happening in the machine, like how many pieces have been produced, for how many minutes the machine has been running since the beginning of the shift, how many stoppages have happened. So the information is really real time and it is available on a shop floor terminal. Similarly, you can also put the data through a cloud using proper security, and then even people outside, the line manager or anybody who is need to be having this information can get this information on their device. It may be a mobile device or it can be a tablet. They can get the same web page using a secure. So that means today we are picking information from the shop floor using simple sensors, processing them on low cost microcontrollers which are available off the shelf, processing them and putting them onto the standard servers, and then interpret the data using dashboards and provide this information almost in real time to the people who ought to take decisions. And here I have given a link, just a small short link with an example of a Python script which is used for running the or picking up data from relays in this case. So there are hundreds of such examples available. You can use any of them, but just to be sure, I have given a reference to this script. So this is the most important slide of my presentation, how you can build your own digital tool using off-the-shelf sensors, relays, Raspberry Pis, and freely usable Python. Python is free. You can use your Python. You can use MySQL, is again a free tool. So you are building virtually everything at a very low cost. I mean, to give an example, for a machine, for this example, what I'm showing, I think we had spent about 14,500 rupees, including that monitor what we have kept there. I think it was a 22 or a 24-inch monitor we have kept. So the whole total cost of building, except the main server, which was of course shared one, the remaining hardware just costed us less than 15,000 rupees. You build a nice tool, at a very low cost and which serves the purpose. So this is what digital is enabling us to do. So this is the crux of my presentation. So I'll go forward and complete it with a few more slides. So once you have the data, then we have to do the maths. I think this is done in the database server, what I showed you. So you simply start step-by-step calculation. Once you get the data from the sensors, so first we compute the availability. Okay, I know the shift was, for example, 8 hours into 60 minutes, so I had 480 minutes, but there were two big stoppages which the operator confirmed through an application, that there was a big setup change which ran for 40 minutes, and then there was a breakdown of 20 minutes. So I lost 60 minutes. So in effect, I had only 420 minutes. So my availability of the machine was only 88%. So I lost 12% of availability because of my setup change and my breakdown. Then next I compute my performance. Okay, this is the one which you use the sensors for, to know actually how many pieces of products were produced and at what time frequency. So taking the first step, I had 420 minutes of time available. My production rate at ideal conditions, I should have been producing 2 parts per minute. And actually, I ended up producing 800 pieces. At the end of the shift, I count I know, because I use a sensor to count in real time. I have produced 800 pieces. Whereas I should have produced 840 pieces. So I lost 40 pieces because of some poor speed. Maybe I was doing some small setup change. I was making a small tool change or a tool dressing, or I had to run the machine at a lower speed because of the poor quality of raw material or whatever it is. So I ran it at a less than optimal rate. So I lost really 40 pieces. So I lost 5% of my performance on the machine. So my performance factor was only 95%. Then I go to quality. Then I check the parts that I have produced. So I had, for example, I have produced 750 parts, and out of which I found 30 to be defective and 20 to be scrap. So I ended up having only the remaining. So instead in the good production, I could only get 750 parts. So my quality rate was only 94%. So all these three things are contributing to my OEE. So my final OEE of this equipment for that shift has been only 79%. So this you can compute in real time because you know the time the machine was planned, and the stoppages when the time the signal was not being received from the sensors, you consider them as stoppages and you ask the operator for the reason, and based on which you put them into the respective bucket, whether it is a availability issue or it was a performance issue. And then at the end of the shift, you also have the quality data coming in. In some cases, in continuous process lines, we can always ask at the end of the line operator. In some cases we do, to say whether the part is okay or not by pressing a button. So you also measure the quality rate continuously, and you can compute almost this is in real time, and then show that you have this OEE. So this is what we had done. In this case, this is an example from a continuous processing cutting line, where we have put two sensors which I blown up, and then I showed you how the sensors capture the data, and the program really computes the OEE in this fashion, from the planned hours to the run hours and net run hours, productive hours, and fully productive hours is the time which I really had to produce good quality parts, which is the real output of the machine. So this we compute, and then this is the screen of the application where the operator confirms the gaps. If there is a loss, then the operator confirms here he selects the reason code, why there was a loss or why there was a stoppage. And then this is the sample dashboard. This is a dashboard of the cutting line. Here you can see, and it is a continuous thing. So first thing, whether the machine is running or not, you get a signal at the top, because once the machine is continuously running, the sensors continuously send data at the desired rate. So if you don't get information for a stipulated time, then you say that the machine is not running. So the red light glows, and then you go and see what happens really, and then you start integrating the data. Then, as you can see here, what is the total time the machine has run, and there is any loss, schedule loss, and is there availability loss? Then there is a performance loss, and there is a quality loss. So you can see shift by shift. We show in our system, we really show we benchmark between the 3 shifts to say really what is the part count and what is the cycle time for each item, and how many pieces were produced, and what is the real OEE of the machine on a continuous manner. So this is the example of a dashboard, and I'll show you one more process where we use a different type of sensing. So here we use a thermal imaging camera. The earlier case, it was a proximity sensor to count the parts, because in that machine, that's what matters. You have to see one item going in and the same item coming out. In this case, it is a furnace. So really, you need to know what is really happening in the furnace, because it's not a quick process where you just cut and then send. Here you do the tempering process. So you need to know what is the load on the bed and the surface area, etc. So for which we use a thermal imaging camera to capture, but the concept is same. So we have a surface load, we have a bed load, how much I could have put on the machine, and how much actually I have kept on the machine because of the shape and size of the part, and then how many real good products I prepared, and then this shows the OEE in this fashion. So this is the dashboard which we built for the tempering furnace, so which shows the surface load, bed load, and the yield of the line. So these are 2 different processes, but as you can see here, almost every item is built with simple low-cost tools. Again, this uses the image processing using a standard thermal imaging camera, and the data goes into a simple MySQL DB, and you process and get the area information, and then you compute the OEE. So there are several such examples which I can go on quoting, but the real thing is that this, as I shown in the PDCA map, so you have to really understand your process, what is the metric that you want to measure, and what is the best tool and method to measure it to get the computation of availability, performance, and quality losses. So this is what is listed here. If and when you want to start a project on this OEE, so you have to ask all these questions. So we just listed these 10 questions to say how to start. Do you have in a process, do you already measure OEE using conventional means? Then do you have written standards? So if not, there is no clarity, it is better to start with some written standard about how to measure OEE. Then are you computing the 3 things like availability, performance, and quality? And do you have reasons for all the losses? You must, because in a computerized system, when you start doing this, there is no point in leaving gaps. So you ensure that you are able to quantify and qualify each loss with proper reason codes, so that at the end of the day, when you have an analysis report, you know exactly what you lost and why you lost. And then your cycle times are measured in real ideal condition, and are you reviewing your losses periodically, and then these are some very basic questions to start in a structured way, so that you can document the project start to end, and then at the end of the day, like after you build the project and you implement it, you can see the improvement that has accrued due to the project, or due to the digital tool what you have prepared and implemented. So this is what I wanted to present. and I'm sure some of you may have questions, so I am ready to take up questions, and I can go back on any slide if you really want to see something in more detail. As I said, this is clearly an example built in our own production environment, and this you can use many of the generic concepts what we have presented here, but you have to really build with respect to your own production process. You have to really build your own method and tool, and you can use the generic flow what we have used here to build your tool and build the dashboards. Thank you. Vimal? Okay, there was a question from Mr. Srinivas Rao. His question was to ask whether we use any software. Did we write any software or use any third-party software? The answer is we wrote software. We wrote two pieces of software. The first one is the Python script, which is running in the Raspberry Pi to pick up data from the microcontroller. It is the program or the script which really interacts with the hardware and picks up the signals and then put them into a database. So this is the first program that we wrote, and I had already shared a link in my presentation, a short link I showed you. I'll go to that part. So here in this slide I am showing, so this is you can see the script in this. This is a freely openable link. We have just shared the script. This is an example where you can use in a Raspberry Pi to read signals from GPIO pins. The second program, second software what we wrote is on this dashboards. So here again, we built our own dashboards. We use .NET and MVC framework using the data in the MySQL software, and then we presented it in a simple graphical form. So both the softwares were written by our internal teams. And there's another question from Mr. Arun Kumar. He's asking, most people calculate without planned data. Is this the correct way? No, I don't think it is the right way. So you always have a norm. We always start with the plan, because that helps you to really show where you have lost. Basically, whether there is whether there was any in the availability part. If you are not even planning to run, that has to be included in the as it has to be captured and included in your reporting accordingly. If you don't start with the planned data, you miss that part. So you always start with the plan, and then you say what is the time that you are planning to utilize the equipment, whether it was fully going to be loaded during the shift or not, and then you start working. So the availability for computing the availability factor, you really need to include the plan. This is my answer to this.
If any of you have any more questions, you can type it out in the dialog box that is appearing.
Yeah, again, there is another question from Mr. Srinivas Rao. He's asking whether we can connect IoT to ERP. The answer is yes and no. You don't normally connect the data in the shop floor directly to the ERP, but you go through the layers, as I showed in my presentation in one of the slides. Typically, you have to go through at least some of these layers. The ERP normally sits in the level 4, and then your IoT is at the level 0 or level 1. So normally you process data within the industrial network, within the plant network, and then sometime you may end with that. If it is for producing a real-time alert, then you may not even go to ERP, because your purpose is to produce an alert in the shop floor to modify the process. But if you are going to capture the production rate, the production quantity through an IoT, then obviously you will want to pass on the information upwards. And typically you may or may not have a MES. In some cases, if you have a MES, the MES is the one which captures the data first from the shop floor, and then MES can aggregate and send it to ERP. So the answer, even SAP being a ERP, they have 2 layers of software, which is one is called SAP ME, which is a manufacturing execution system, and then they also have something called SAP MII, a manufacturing intelligence. So, and that is what is really getting connected to the line, really, the sensors or the hardware. So even SAP has 2 layers of software between the ERP layer and the level 0.
Mr. Kumaradevan, Mr. Arun Kumar has asked a couple of questions. He's asking, so
Yeah,
can we show unplanned runtime as an accountability and not a OEE?
Yeah, this is it's a philosophical question. I mean, I cannot say yes or no. So in what actually we try to do in all our endeavor is to capture the losses by time. The first availability and on the availability part and the performance part, using this tool, we know how much time the machine was not running, or how much loss was happening due to loss of speed against the rated production. And then we ask the operators to provide information with respect to what went wrong, why there was a stoppage or why there was a loss, and what is the recent code. And then we use it to supplement the OEE, but the OEE is always computed as pure numbers based on the actual data captured, and the operators and the line supervisors really provide reasons for the losses, which we use for continuously analyzing and improving. The other question is, do we require to stream data from CNC as a... That question I don't understand. To stream data from CNC as people expected. I don't understand this question.
Okay, probably we'll ask him to. Arun Kumar, Mr. Arun Kumar, if you can be a little more specific on the question, will be helpful. Mr. Srinivasa Rao was asked, what is the ideal implementation time?
See, if you do your planning well, if you have your that 10 questions what I listed and document what you want to do and select the right tools, you should be able to, from scratch, you should be able to complete the whole project in 15 days. This has been our experience. When we start with the new equipment, today we can actually do it in 7 days or something, because we already have all the basic knowledge and infrastructure. But even with the kind of inputs that you have today, if you start from scratch, you should be able to do it in 15 days, because we are not talking about very high level transaction processing. You need to know how to capture the data, store, then do simple computations and just present. And today all these graphic elements and all, they are freely available on even on the web. You have several, you don't really do programming to prepare a graph or show a speedometer. So there are standard components available. You just plug in and then pass on the data, and they do the rendering, and then they show you a nice graph. So with a well equipped IT team, programmers in your team, you should be able to start and end in 15 days.
Mr. Arun Kumar has another question. What is the best practice to account an operator against asset performance?
Again, this is a question which is very difficult for me to answer. Asset performance, again, there can be two parts. One, loss of performance due to the condition of the equipment or whatever. The second one can be the skill. So while I think over a period of time, as you measure these losses, okay, like there are a loss of speed, there is frequent tool wear, or there is so it may be while if you do a proper an YY analysis for each type of loss by a Pareto, and then try to understand the reason, then slowly you will start attributing to either it's the condition of the equipment or the quality of maintenance activities that we do, or finally to the skill of the operator. Finally, while the word accountability I'm not very comfortable, but we use if then there is a loss of skill or a lack of skill, we use this information to train the operator. I think one should look at that way, and there is no universal answer for directly attributing loss of performance or asset performance to just the operator accountability alone. This is my view. The next question is to CNC position data and load data. I don't know what that means. Is to CNC okay? I'll go to the next question. There is one from
Mr. Manikanda Babu is from Lucas TVS. Yes, he's asked a question. Industry 4.0 does not stop with just automating manual data capturing. We feel to become smart, some amount of intelligence is built into eliminates manual intervention or dependence on certain common jobs. Example, the system should be capable of detecting automatically the availability and performance of quality data. Also, some amount of intelligence to give correct or give instruction to operator on what to do.
Absolutely, this is a very correct statement. I fully agree. I fully agree with the statement of Mr. Manikanda Babu. The Industry 4 is all about it's not a open-ended system, right? It's closed loop, and we don't capture this information just for presenting or analyzing. The idea will be to slowly build this intelligence back into the process, self-adjusting, self-optimizing networks. But today's topic was merely measuring and presenting. It is not really a end to all. Like if there is a loss of performance, as Mr. Babu correctly put it, we should be able to pick up. So today we have such projects. We have, for example, we have a project in which on a glass grinding machine, we monitor the spindle load continuously. We know what is the ideal current that should be taken by the spindle when it is in a good condition, when the grinding wheel is in a good condition, grinding normally. And the moment we start seeing the excess current drawn, then we know, yeah, there is a problem. Probably the wheel needs addressing. So over a period of time, by analyzing this current drawn by the spindle, now we are able to sense when a wheel is due for dressing. So this is exactly what the Industry 4 is all about. It is not just sensing or picking up data, but being able to analyze at the edge near the machine, and then provide feedback, and then perform the corrective steps using the data that you have captured. I fully agree.
So the next question is from Mr. Srinivasa Rao. He's asking, is it possible to connect all the machines in our plant and get OEE for entire plant?
No, yes and no. Technically, yes. But I think you will, it depends on, again, the factory. If you have a if you have discrete machines. In our case, for example, we are a process industry, end to end. So we put raw material on one side, and then we get the finished product on the other side. So in our case, we can simply say this is the total overall OEE of the whole plant using a simple mechanism. But if you have a complex setup of discrete machines with different production cells producing different items, so it is not easy. So obviously you will want to start at the lower level, at the equipment level, and then slowly build up. And many of the other things you can actually compute in a hierarchical way, and then of course you can come to from a machine to a line to a shop. You can really take it up. It is technically possible, I would say, but we don't start with that kind of a vision in mind. We do for local improvements. You start at an equipment level, you optimize, you improve. That's how we see it. There was again Arun Kumar has qualified.
Yeah, Arun Kumar
is
asked. Yeah, he's asked whether computer numeric control is used to. His previous question was: is used to position data or load data?
Still, I don't understand what the question is all about.
Okay,
I'm really
Mr.
sorry.
Arun Kumar,
As I understand, yeah, he can write to me in more details.
Maybe we can take this offline probably. The next question is from Mr. Rafi Rabia. He's from KH Exports. Would like to know whether OEE can be startup in our factory for an automated sewing machine, so that machine efficiency can be calculated.
Yeah, I'm sure. I'm sure this is a good case to do. Definitely, this can be done. But if it is a sewing, I'm not okay. There will be many. I'm sure it is not a continuous process, and it is not an automated process, as I understand. Because I don't know, I have not deeply studied or visited a factory. See, the OEE, when there is not, I think according to me, the sewing process where you have a lot of manual interventions. With every few seconds, the operator may be intervening to do some direction change or whatever. So the OEE is more towards if you have, at least I would say 80% of your time is machine is in auto mode, and 20% a rough rule of thumb I'm giving. So it can be, this kind of automated measurements can be very effective at that level. But I'm not sure in a sewing machine. You have to really study how many minutes the machine is actually running and how many minutes the machine is not running for various reasons. You may stop it for various reasons. The operator may stop it for various reasons. So it may be very difficult for you to. One thing that you can do is you can really definitely you can measure the availability. There's no question. It's easily measurable because the machines are running using motors, and you can always integrate, and then end of the shift you can know how many minutes, seconds the motor was actually running, so the machine was actually running. But whether that data alone is enough to effectively give a OEE, I'm not very sure, because if you know that a machine has been running for 4 hours and the motor was not running for 4 hours, unless you're able to attribute the reason for the 4-hour stoppage in minute level, because there will be many stoppages, if I understand. Whether this measurement itself will be very useful or not, I'm not sure. But to answer your question from a technical perspective, definitely yes, it is much easier to do on a sewing machine.
Srinivasa Rao wants to know what is the output format.
The output format is usually, for example, from a Python script, the data comes out in and gets into the MySQL database directly. So all the formats are in, I can say you can take it out in a text format from any of these databases. So the first time the electronic signals, zeros and ones, are converted, or using the Python script, because it reads the state of the memory, and then accordingly it puts a 0 or 1 and the timestamp into the database. So from there it's all in the database, and it is all in human readable form. And from the database, the output format on the dashboards, it can be on web pages, as I said, or it can be mobile pages, or it can be even SMS alerts. Sometimes we send SMS alerts if there is going to be an unscheduled stoppage when it is not expected. So it can be the formats can be anything as you please.
Yeah, Mr. Arun Kumar has explained his question. Do we require to stream computer numeric control or PLC access position data and load data for IoT, as people are expected to do so?
No, I'm sorry. I don't think I can answer this question.
Okay.
It's too much for me, because streaming CNC, PLC access position data and all in real time from a OEE computation perspective, I don't think it is really required. See, in OEE, what we are really computing is the availability, which is basically start. We monitor basically start stops when the machine is running, when the machine is not running, in simple terms. And when the machine is not running, it is not available. So I try to attribute reasons through different mechanisms why the machine was not running, whether it was a planned shutdown or a unexpected breakdown. And then we normally measure the output in terms of quantity, what it ought to be producing and what it actually produced. So that we attribute it to the performance loss. The third one is what is the good quality and what is bad quality. I think most of the industries, most of the companies are computing availability, performance and quality in this manner. And I don't think you really need to stream the access data or position data. I don't know how it really matters in a OEE computation perspective. I'm not able to get a perspective on that.
Looks like everyone is done with their questions. Any of you all have any more questions, participants?
Yes, Mr. Srinivas Rao, if you have a question, you can ask.
No, he says he's done with the questions, I think.
Then he has a question. He put yes when you said we
actually have a class of students from the IIII TDM, the Kanchipuram, Professor
Okay.
We have students from their institute also listening to the webinar.
Okay.
Okay, I think everyone is done with their questions, sir. Mr. Kumaradevan, thank you very much for this really in detail, so much explanatory presentation for the afternoon. Okay, there's one more question, I'm sorry. How to calculate OEE for machine tool with multiple component?
Yeah, it's okay. You have a step-by-step process. Multiple components may be produced during a shift. I don't know whether you're talking about producing multiple components at the same time. I'm not very sure. Whatever may be the type of output, for each component that you produce, you have a planned cycle time. Okay, or if you are always producing a set, in case in a press tool, you may produce the same punch can produce 3 different type of products in one shot. So, but the cycle time for all the 3 put together is X seconds or X minutes. So ultimately what we are computing is what is the planned cycle time per component or a component set, and then what is the actual cycle time based on what actually you produced during the available time. So multiple components doesn't matter. Multiple components, if you have a combined cycle time for a set, then you treat it as a set. Or if they are producing sequentially one after the other, then you do it, you sum all the cycle times of all the planned cycle times of all the components and then use the standard. So it's not a problem. Either way you can. It's only that's why this method and how you are going to really compute is very, very unique to your thing. So the basis is very, very simple. So you need to measure the cycle time. You need to measure the availability, and you have to adapt it to your own situation. Since the base formula is very, very simple, you have to only adapt your situation to fit this base formula. It is no company calculates anything differently from what I have presented in terms of the OEE. So it is up to you to design your own method based on the first principles. How do I compute the available time? How do I ascertain the reasons for stoppage? How do I count the production? And how do I take inputs on good production, bad production? So these are the only 4 things that you need to be worried about, and all the 4 may be automatically computed or automatically sensed, or you may automatically sense 3 and maybe still take 1 as a manual input. Doesn't matter, but the first principles remain the same.
Okay, thank you, Mr. Srinivasa Rao. Thank you, Mr. Arun Kumar. Both felt the session were very good. The feedbacks are here for you to see, sir. Mr. Kumaradevan, thank you very much for, as I said, it was a very in detail session that we had for the past 1 hour. For the benefit of all the participants, this is a series of webinars on different topics pertaining to manufacturing and digital excellence. Every 3rd Friday of the month, we have a session from now on to March 2018. The next session will be on December 15th on remote monitoring and maintenance with a different speaker. We will be sending you all details on that webinar also. If you guys are interested, please do log in, send us your interest, and we will register you. Thank you, Mr. Kumaradevan. Thank you for the session today.
I thank all the participants, all from the industry. I think we had good interaction, and many of you may know many of what I have said intrinsically. So I am really happy to have shared my experience, and I thank the students and the faculty from IIIT DM. I'm really pleased to share my knowledge, and then I also thank CII for providing me this opportunity, and Dr. Sudhir, I think he has put a message now. In fact, this session was planned jointly. He was one of the key person to decide the topics for this session, and I'm very happy that he's participating in this. Thank you, sir. And I'm available for any comments or any communication through CII. I can always be reached, and as Singomen will be very happy to share our knowledge and experience in any forum. Thank you very much.
Thank you, sir. Thank you all.